Hello and welcome to this tutorial on implementing vision transformers for image classification. Today we'll implement a vision transformers from scratch using PyTorch, then use a pre-trained model for inference. Let's get started. First, let's set up our environment. Here's the code to import everything we need. We'll be using Torch, the core PyTorch library for tensor computations and neural networks. Torch.nn contains neural network layers and loss functions. TorchVision.transforms provides common image transformations, and PIL, Python imaging library, used for opening and manipulating images. Make sure you have these installed in your environment. Now, let's implement the core ViT architecture. We'll start with the patch embedding. This patch embedding class takes several parameters. IMG size is the size of the input image. It assumes that the images are square. Patch size is the size of each patch. In channels is the number of input channels. For RGB images, the value of input channels is usually 3. And embed dim is the dimension of the embedding space. It calculates the number of patches based on the image size and patch size. And here it defines a convolutional layer that projects the image patches into the desired embedding dimension. The forward method uses a convolutional layer to project patches into the embedding space, then reshapes the output. Next, let's implement the transformer encoder. This class represents a single encoder layer in the transformer architecture. It defines a multi-head attention layer to learn relationships between patches. It defines two layer norm layers, norm 1 and norm 2, for normalization. It also defines an MLP sublayer with GELU activation for nonlinear feature extraction. And lastly, it defines a dropout layer. The forward method applies these components in sequence, with residual connections. Now let's put it all together in the ViT class. This class defines the complete ViT model architecture. This ViT class combines all the components: patch embedding, class token and positional embedding, stack of transformer encoder layers, and MLP head for classification. The forward method processes the input through these components sequentially. Now that we understand the architecture, let's load a pre-trained ViT model. This code imports the pre-trained ViT-B16 image classification model from Torch Vision, loads the corresponding weights pre-trained on ImageNet, and sets the model to evaluation mode. The B in ViT-B16 stands for base, and 16 refers to the patch size. Let's use our model to classify an image. First, we need to import some libraries. Requests library allows us to make requests to web servers, in this case, to download images from URLs. This line imports a class called bytes.io from the IO library to create an in-memory stream of bytes, which is useful for handling downloaded image data. Here we are importing the image class from the Pillow-Friendly Imaging Library, PAL. This library allows us to work with image files. And here we are using PyPlot module from the Matplotlib library, which allows us to visualize images and plots. This preprocess image from URL function processes the image from the given URL. It takes two arguments: a string representing the web address of an image, an optional size parameter specifying the desired final size of the image after preprocessing. This compose method creates a sequence of image transformations typically used for deep learning. We are passing a list of transform objects as arguments. Transforms.resize resizes the image to the specified size. Transforms.centerCrop crops a square region from the center of the resized image. Transforms.toTensor converts the image data from a PIL format to a PyTorch tensor format, suitable for deep learning models. And Transforms.normalize normalizes the pixel values of the image based on the provided mean and standard deviation. This helps improve the training and performance of the deep learning model. Then we download the image here. It then opens the downloaded image data using open method and converts it to RGB format. Finally, it applies the defined transformations to the image, returning two values: the pre-processed image tensor ready for the model and the original downloaded image. This classify image function predicts the probabilities of different categories. This function takes two arguments: a pre-trained image classification model and the pre-processed image tensor created by the pre-process image from URL function. It uses the no-grad context to disable gradient calculation during the forward pass of the model, since we're not training here. It feeds the input tensor through the model. The model likely outputs a vector of probabilities for each possible class, representing how likely the image belongs to each category. Here we are converting the raw probabilities into a more interpretable format, normalized probabilities summing to 1. It then uses top K method to find the top 5 most likely classes, based on their probabilities and their corresponding indices. Finally, it iterates through the top 5 results, using the class indices to access the corresponding class names from the model's predefined categories list, and returns a list of tuples, each containing the class name and its probability. And lastly, we process and display images in this function. It takes an image URL as input. It calls the preprocess image from URL and classify image function to get the preprocessed image tensor and the original image. And here we are displaying the original image and printing the top prediction and all the predicted classes with their probabilities. All right, now that we have everything set up, preprocessing, image classification, and visualization functions, it is time to use them. Here we have a list of image URLs. These are the web addresses of the images we want to classify. By the way, I have taken these images from this GitHub repository, contains one random image per ImageNet class. I choose some random images from here to test. All right, back to the code. Here we have a loop that iterates through each image URL in this list. So for each image URL, we call the process and display images function, passing the current URL as an argument. So as we run this code, it will process each image URL one by one, performing classification and displaying the results. As we can see in the output image of the first URL indigo bunting, we can see that indigo bunting has the highest probability, 0.8918, followed by goldfinch, 0.0010, and so on. The probabilities decrease as the model becomes less confident in the remaining predictions. Also, we can see that the top prediction is indigo bunting with a probability of 0.8918. Top prediction represents the class with the highest probability according to the model. For all other images, we get similar classification results. For this image of broccoli, we get the highest probability of 0.8948. Similarly, we get the expected probabilities for the image of espresso and the image of lakeside as well. And there you have it. We've implemented a vision transformer from scratch, loaded a pre-trained model, and used it for image classification. ViTs are powerful models that combine the strengths of transformers with computer vision tasks. I hope this tutorial has given you a solid understanding of how to work with vision transformers. If you found this video helpful, please like and subscribe for more AI and deep learning content. Thanks for watching, and happy coding!